Yesterday, we actually started this course, and as we all know, it is simple ICTP research in Pierre's lecture on theory of partial differential equation. Let's just have a recap of what we did yesterday. We look at, this is the summary of what we are going to be looking at in this course. And yesterday, we started the section 1, and we even entered the second section. And in section 1, which is our first order partial differential equation, we looked at the introduction, where we explain what we understand by the dependent variables, by the independent variables, the dependent variable, and then the derivatives, which are the components that made up the differential equation. And we say that the u that appear here is the unknown function, and these are the derivatives. And then again, we talked about the types of first order PDEs, where we have the linear first order PDE, the quasi-linear, and then we talked about the non-linear first order PDE, and then we move on to look at the derivation of partial differential equation, where we talked about elimination of these two constants so that we can have our PDE. And then again, we look at this, then we look at the derivation, where we look at one or two examples like that, and then again, we move on to the derivation of equation 1.1.11, and then here we gave an example on how to derive a first order differential equation. Then we look at the solution of Lagrange's linear equation. This is the Lagrange's equation. Yesterday it was derived, and then we moved on, prove this, we showed this proving. Then we also look at the general method for the solution of first order partial differential equation. We talk about the Chapt's method and then the Jacobi's method also, and then the relationship between them. And then we move on to look at the two methods in details, and then we then talk about the determination of these G2 and G3 function. Then we enter into the section 2, where we start our discussion on partial differential equation for second and higher orders. And here we look at, this is the general form of the differential equation under consideration. And then we move on to talk about the method of solution. Here we'll talk about the complementary function, and then we show the proof of this. And we move on, and I think we stop somewhere around here. So today, we are going to continue from here by looking at the particular integrals. How do we generate our particular integrals? And what are the guys? What are the guys to generate our particular integral? Of course, we know what we mean by particular integral. Particular integral will always arise once the differential equation is inhomogeneous. That is, if this f of x is not equal to 0, then surely we know that the differential equation is inhomogeneous. It's inhomogeneous, and we have to talk about how to obtain the solution given that this is not equal to 0. First, we know for the first part, we are going to solve this, which is the homogeneous part. Then we now look for whatever it is that is going to be our particular integral, we resolve it, and then we add the two solutions together in order to give us the solution to the differential equation under consideration. So method 1, we say that if the operator f, which is given here, is a reducible operator, then the particular integral is of this form. 1 divided by this multiplied by this. Then by the time we put them together, we are going to have what we have in here, where this j starts from 1 to m. And this m is determined by the order of the differential equation. Let's look at the general form of the differential equation. This is the general form of the differential equation. So we can see here. So this m will be determined by the order of the differential equation. And then again, so if that is the case, then what do we do further? Once we are able to determine what our m is, the next thing is just for us to obtain what our assumption is going to be for f of d, d prime. Then we start by implementation of the inversion operation from the last factor on the right hand side. So here now, once we are able to determine our m, the next thing we are now going to do, we now do this assumption by multiplying this by the inhomogeneous part, and then we equate it to an arbitrary function, let's say g of x comma y. And of course, we know this equation in 2.11 is equivalent to what we have here. Now, by the time we resolve this, by the time we expand this, we can see that we are going to have a first order differential equation here, whereas this gamma m multiplied by g is going to be added to the inhomogeneous part of the differential equation, though in this case it's going to be negative because by the time we move it to the other side, it becomes negative. So you can see here now we have a first order differential equation. So here now we can just obtain the Lagranges of this equation, which is given here. Then by the time we take these two pair, the x, the alpha m minus dy, the beta m, we are going to have, this is what we are going to have. We are going to have everything here to be equal to 0. Then by the time we integrate this, we are now going to have our beta mx minus alpha y to be equal to c. That is the integral of this 0. We know once we integrate 0, we are going to have a constant. Then the next thing we are now going to do is we are now going to pick the other pair with respect to dx, which is dg divided by f minus this g to be equal to dx divided by alpha m. So by the time we cross multiply here, we separate this differential equation. We are going to have it to be in this form. We can see that this differential equation has been successfully separated here. So here we can see clearly that g here depends on x. So now, the next thing is, how do we now solve this first order differential equation? We are now going to make use of the integrating factor method. And once we have the differential equation in this format, the integrating factor we are going to assume is going to be of this form. You can see here, this here is the coefficient of what? Of g. Then we have our exponential, the integral of this to be equal to exponential, which the integral of this surely is going to give us our exponential gamma m divided by alpha m. Then we have our x. So this is what we are going to pick as our integrating factor. And then by the time we move forward now, then we can now, since we already know what our integrating factor is, then we can move forward, and then we are going to have, this is what we are going to have by the time we use the method of integrating factor. So this is what we have, and then we can now carry out the integral of what we move this to the other side so that we can have this equation. Then the next thing is we are now going to integrate whatever it is that we have here. This actually depends on whatever it is that is the differential equation. So we are going to have this, and these alpha m must not be equal to 0 so that this equation here will be defined. So if you recollect, you see that what we pick was the pair. That's the second pair that we pick was for, this is what we pick. We pick this, dg dx. Then the next one now, we're now going to pick, which will also follow the same process, is going to be with respect to y. So that right time we follow the same process as we have done here. We are going to obtain this. This is what we are going to obtain. So we observe that no arbitrary constant is introduced because pi does not contain arbitrary constants. So yes, we are not going to introduce any arbitrary constant into this differential equation because the particular integral does not need to admit that was equal. Already here, we already have enough constants here. So it therefore follows that our 1 all over, now we have obtained what our g is. So the next thing we are now going to do is to substitute that our g back into the equation where we started from. So this way, we operate from the remaining factors from right to the first on the left in turn to finally obtain our pi. So we'll now continue from where we stopped. Now we're now going to look at the second possibility, which is decomposing the operator this into partial differential equation. That is, this is what we already have before from here. So what we have here, this is what we are going to decompose into partial differential, into partial fraction. So by the time we do that, of course, we know from elementary math, we are going to have a constant on each and every one of them, a1, a2, up till am, depending what the value of am is. So that is what we are going to have, and then we can now have this, and then perform the inverse operation time wise of this differential equation. We have, so now we then perform the inverse operation time wise to obtain the required particular integral as demonstrated in the following step. So here for the first one, we are going to have, we have this, which is the first one, just as we handle the other one. We are going to obtain, by the time we do that, we are going to obtain these auxiliary equation, and then we take it pair by pair. The first pair here, which is dx the alpha 1 equals to dy the beta 1. This is the same thing as what we have here. By the time we cross multiply this, then we then integrate this particular equation so that we can obtain this. Of course, we know the integral of 0 will give us a constant. So similarly, we have that dg divided by f minus gamma 1 of g is equal to dx divided by alpha 1. And by the time we have that, then we are going to separate this equation just as we have done before. So this is the differential equation we have. And then again, of course, following the same process as we explained earlier, we are going to introduce the integrating factor. Of course, we know that the coefficient of this g here is gamma 1 divided by alpha 1. So the integrating factor we are going to assume is going to be of this form, which is going to be this. These are for gamma 1, alpha 1. So the same thing will apply, okay, just before then we can now go back to the differential equation so that we introduce our integrating factor, of course, from elementary math, and then alpha 1 surely must not be equal to 0 so that this equation will stand. Then by the time we do that, then we can then resolve these integral here. Mostly it will just fall into, I think, integration by parts, which we can easily resolve whichever differential equation it is. Then we have this. Then similarly, please mute yourself. So similarly, we have our g now will now be equal to what we have in here. And then the expression for the pi is therefore giving us this. So the same way we obtain for the first one, for alpha 1 gamma 1, the same thing we are going to do for alpha 2 gamma 2 till gamma m alpha m. So we are going to put everything together, more like the linear combination, and then of course we have these constants there for each and every one of them. So we can see clearly that we can, by the time we obtain we obtain the solution for each and every one of them, then we put them together. Of course, if it is just a second order differential equation, it's not going to be as long as what we have here, or even the first order is not going to be as long as what we have here. But in this case, we are just talking about in a general situation. So by the time we put everything together, of course, we are going to do it both ways. We are going to do it for the first pair, and then we also do it for the second pair. That is for when g is depending on y. So the first one is when g is depending on x. The second one is when g is depending on y. So by the time we put the two of them together, we are now going to have this as the summation. So the first one, so the first one here, we have this. First one here, we have this for x, and then we have this one for y. And in each case, for the first one, alpha j must not be equal to 0, and beta j also must not be equal to 0. Now, what happens if we have some special cases? Yeah, of course, there is possibility for us to have some special cases. Now, we recall that the particular integral in 2.6 that we discussed is, of course, is giving us this. Then, and this is determined almost the same way as that of ODE. So the inverse operator may be expanded using the binomial theorem, and therefore performing the integration of this is d dx, and then this one is d dy. That is the inverse of d dx. This is the inverse of d dy. That is with respect to x and y, sure. Then the particular integral corresponding to certain special functions may be obtained by much shorter method than the general method. So in this section, we note the following rules. And what are the rules? The first case is when we have our f of x. Mostly it's just going to be our f of x that will change. So supposing we have the first case here, we have f of x to be exponential ax plus by. This will be 1 all over f of a comma b exponential ax plus by, provided this f of a comma b is not equal to 0. That's the first case. Then the second case is where we have exponential ax plus by multiplied by another function, say phi of x comma y. So if we have this kind of case, then we are going to have our exponential ax plus by to be equal to 1 divided by, then we now introduce this d. That means our derivative now, we are now going to add a and b to, we add a to d, and then we add d prime to b, so that we can have what we have here. And phi of x, of course, is just an arbitrary function. It can just be anything. It can be any function. Then for case 3, if f of x is equal to a comma b, which is equal to 0, if f of a comma b is equal to 0, in case 1, that is this case, then the pi is obtained as follows. So in this case here, what we are now trying to say is that what happens if this f of a comma b is now equal to 0? Of course, we know there is going to be a little problem here, because this will surely be undefined because of the 0. But what do we do in that case? In that case, we are going to have it as 1 divided by f of d comma d prime exponential ax plus by dot unity, and which is still the same thing as this. And then we apply case 2. That is, we are now going to add a and b to this d and this. Then we have the fourth case. This is when we have our f of x to be cos ax plus by to be equal to 1 all over f of d square comma d prime comma d prime. You know, this is more like a double quadratic. That is, in this place, this is a second order. You can see that it is second order along x. It is also second order along y. So if we have this kind of case, so this is what we are going to resolve the differential, our pi into. And then, of course, we can take this as a and take this one as b. By the time we take our d dx as a and d dy as b, this will surely be resolved into what we have here, provided this is not equal to 0. Because once it is equal to 0, that is on introducing the a and b, once it is equal to 0, this will be undefined. But what happens if this is equal to 0? Then in this case, of course, it will fail. That means we'll have to look for another thing to use. Then we don't compute the pi by considering the real and the imaginary part, which means in that case, if this is equal to 0, then we'll have to split it into 2 by introducing a complex function. We are going to, of course, we know this is now a complex function. And by the time we resolve this pi, we are going to have it in both real and imaginary. Then the fifth case, here now we have, supposing our f now is just the product of the independent variable. The product of the independent variable to some certain power. So we have the whole of this to be equal to f of d comma d prime to be equal to f of d comma d prime all inverse, and then we have x to the power of m. Then these in this case we apply the binomial theorem to the inverse operator, then operate on x, m, and ym. And these methods are evidently shorter of obtaining the respective PIs. So please mute yourself, please. So that's what we have for this. Then from here now, we can now move to the next section. So now let's look at our next item, which is partial differential equation of the Cauchy-Euler type equation of the form Cauchy-Euler type, the PDE of this form. Here now, if you look at it, this PDE here is quite different from what we have been seeing before. Here now you see that this PDE here, the derivative, all have, look at the coefficient x. This one has a coefficient of y. And of course, it is also the Cauchy-Euler type of differential equation that we have been looking at since. So in this case, we make, when we have this kind of differential equation, what we are going to do is, we are now going to introduce some variables in order to reduce the differential equation to what we can actually manage. And how do we do that? Now we say that where f is a polynomial in the indeterminate xd and yd prime. So in this case, we make the following transformation. We take s to be equal to ln x, t to be equal to ln y, and then we take this theta here to be our dds, and we take phi to be our d dt. So now what do we mean? It is therefore immediate from 3.2 that xd u, that is this, xdu, of course we say that our xd is the same thing as what? As this theta. So we are going to have it to be this. Then x square d square u, that will give us what we have here, theta in the bracket of theta minus 1 multiplied by u. Then to the power of 3, this is what we are going to have like that. If it is to the power of 4, we are going to have theta in the bracket of theta minus 1, theta minus 2 to theta minus 3, like that. And same thing will happen for y. The same thing is going to happen. The only thing that is going to change here now, we are now talking of the function here is now phi, but not theta as we have here. And then also we have all this. So if you substitute all this, what we have in here into the 3.1, which is the main equation, then the equation transforms into a linear equation with constant coefficients, this and this, as the new independent variable, which means the independent variable x and y have now been transformed into theta and this phi. So let's see how we can transform this differential equation that look very ugly here. Let's see how we can transform it to what can be easily handled. Now, if you look at it very well, all we just need to do, we know what our x squared d squared is from here. That's this. And we know what xyd is. We also know what y squared d prime square, we know what it is. That's this. And then we have this. We also have this. All we just need to do is just to substitute into what we have. And then again, of course, we have said it, that our x is, s is going to be taken as ln x, and t is going to be taken as ln y. So by the time we substitute all that into the equation, we then observe that the PDE is of Cauchy-Euler. So by the time you substitute everything in there, of course, you are talking, we say that s is equal to ln x, and y also, t is also equals to ln y, but we are looking for x. It means we are going to take the exponential of both sides. And once we take the exponential of both sides, then we are now going to start having exponential s and exponential t, like that. So this is what we have here now. So we have using this in this, then we obtain, by the time we now substitute all the parameters into that differential equation, then we have this. And then the differential equation, by the time we expand this and do all the elementary math that is in between, the equation will reduce to something of this form. And this is the same thing as what we have here. And you can see this differential equation here is what can be easily handled, because this is all the same thing as this theta minus 2 phi multiplied by another theta minus 2 phi. And then you can see that this is just a linear differential, just a linear differential equation with coefficient. So same thing, we can look at this example also. We can also reduce this by introducing all these parameters into this differential equation. And by the time we do that, we will see that, supposing here now we assume our s to be equal to x upon 2, because here you see that what we have here, they are inverse. The coefficients here are inverse. They are not like the other one that is just direct. So here now, we take our s to be equal to x squared upon 2. And please mute yourself, please. Please mute yourself. Please mute yourself. So now, we are now going to look at the first one. The first one, let's look at it. Du dx, this is the same thing as du dx dot dx dx, because this dx here will cancel this and we'll be back here. And then we know that, and this, the whole of this here, by time this and this surely are the same thing. And here, from our earlier discussion, here now we say that what? Our dx is equal to x. So here now, we are now going to have this to be equal to this, or we say that du dx is equal to 1 upon x du dx. Then the same thing we are going to have for this. This is the same thing as du dx, and this is equal to 1 upon s. Of course, we know that all we just need just to bring the whole of this, then we'll bring it here. Since we already know what we already know what du dx. So all we just need to do is to bring in what our du dx is. Our du dx is 1 upon x du dx. So we'll just introduce it in here. And by the time we do all this, we are going to have 1 upon x all square di squared x square minus this to be equal to di squared u di s square. So this similarly we are going to do to y also, but here now, of course, this is what we are going to have at the end of the day. So we are now going to introduce all these things that we have been able to obtain into the given differential equation, which is this differential equation. And the whole thing is now going to reduce to a function of just a function of this difference of 2 square with the differential equation given. Of course, there is u here. Sorry. By the time we substitute it in here now, this is theta square minus 5 square of u. We know that this one is just straight difference of 2 square. And once we have this, there is u here. So once we have this, easily we can solve this differential equation. Then second order PDE with variable coefficient. Now let us look at it. What happened if these PDEs were considering of this form? What do we do? Second order PDE with variable coefficient definition. A partial differential equation with variable coefficient is that which contains at least one of the partial derivative of the second order and none higher than the second. This is simplified if we consider the case of two independent variables, and we shall define the following as this. Here, of course, from yesterday we were able to establish that our P is equal to du dx and Q is taken as a du dy. So we'll still make use of that assertion in this particular section. So here we assume our R to be equal to di squared u di x square, and by the time we resolve this, we have it as a di p di x, because here now, sorry, the mouse is not okay. So here now is just like by the time you take another derivative of this, we are going to have it as di p di x, which is this. We can take it as R. Also, our S, by the time we differentiate this du di x with respect to y, we are going to have it as di squared u di x di y, and everything will now give us what we have in here and can be written as this also. Then the same thing for this, the whole of this, we say that, here now we are supposed to have Q is equal to di u di y already. So here now, di p di y, di p di y is the same thing as di x of di u di y, and then we have all these. Of course, we know that by the time we take di u di y, this is the same thing as q. So here now, by the time we resolve this one to be q, what we are going to have is going to be di q di x, and we have our t to be equal to di squared u di y squared to be equal to di y of this, and then we have everything here to be equal to di q di y. Then our discussion shall be limited to that of the variable coefficients which are of first degree in R, S, and T. Yeah. That means this R here, the S here, and this T here are just going to be for first degree. We are not going to take for higher degrees because we don't really have much time, so we'll just limit ourselves to what we have here. But yeah, of course, you people are free to go into textbooks and then exploit more. Well, so here now, we say that these R, S, T, and V are in general function of R, X, Y, P, Q, and U. And this will be illustrated by a solvable inspection. Now, let's assume you have this. We are told that we should solve S equal to 2x plus 2y. And of course, we know that this S here is a differential. So what do? We just introduce what the differential is. We already say, oh God. So the PDE is given by our S is di squared u di x di y. So this is what we have. So S is equal to 2x 2y. Then we have di squared u di x di y to be equal to 2x plus 2y. And for us to obtain the solution to this differential equation, all we just need to do is to integrate with respect to x. When we integrate with respect to x, we add a coefficient of we add a function of y. When we integrate with respect to the other one, we add the coefficient of we add the function of the other variable. So here now, if we integrate with respect to y, we are going to add the function of x, which is h of x. And then again, for us to obtain this u, we integrate this again with respect to x. And then we now add a function of y, which is what actually gives rise to this. So here now, this is what we have. And then pending the condition given, we will be able to obtain what h of x is, and what phi of x is, because phi of x here is equivalent to the integral of h of x. And then also from there, we should be able to obtain what this g of y means. That is, we need additional information for us to be able to obtain these two functions. But for now, as it is given, this is what is required. So we note that 3.5 is a second order quasi-linear PDE, and it is linear if it can be put in this form. Of course, we know we discussed what a quasi-linear is yesterday. Sorry, it's 3 p.m. So we'll be back in let's say 10 minutes. Then we'll continue from here. Thank you all. We'll now continue from where we stopped. At least we've had enough break. So now let's look at these two differential equations. We observe that we say that here now we now want to look at the differential equation with a variable coefficient here. You can see, look at this differential equation, the first one. You can see the coefficient of this term. You can also see the coefficient of this term. You can see the coefficient of this term. You can see this one is quasi-linear because it has this as a coefficient of the derivative. It is quasi-linear because of this, and you also, this differential equation is also a quasi-linear differential equation, just as we discussed them yesterday. So now we are now going to look at the next item, which is the Monge's method. So in this section, we shall discuss the Monge's general method for solving these differential equations. Now, in which all these are functions of this and that. Then, sorry. Okay. So Now, let us look at these transformations here that we mentioned earlier. This is a second derivative with R here is taken to be the second derivative of u with respect, which is also the same thing as di phi di x. The same thing with this s. This is what we used to solve the other problem that time. And then we have t to be taken as this. So from 3.7, we recall that dp dx, that is by the time you take the total derivative dp, of course, we are going to have, this is what we are going to have, dp dx dx plus dp dy dy, and everything is equal to r dx plus s dy. Already we know that our dp dx, we know that our dp dx is the same thing as di squared u dx here, which is equal to r. And then the same thing with dp dy, we have already been able to show this. So we have the differential equation to be reduced to this form. The same thing goes with this also. We already know that our diq, we already know that we know that q is diu, q is diu dy, sorry, there is a typographical error here. And then here now we are going to have, we have our diq dx here, dx, then plus diq dy dy, and everything here is equal to s dx plus t dt. So from 3.9, that is from this particular equation, then we can resolve that r is equal to dp minus s dy divided by dx. That is by the time you divide through by dx. So we have, that's what we have. And then we have our t to be equal to what we have in here. So if we substitute what we have here, these items here in 3.11, if we substitute them into 3.7, the differential equation will now look like this. Or by the time we clear the denominator, the differential equation can look this way. So that is, then we can then put them together. That is, we group the differential equation together. We can see what we did here. These ones are all the ones with coefficient of s. We can see how we group them together. So if there exists a relationship between x, y, u, and p and q, such that the terms in the parentheses in 3.11 vanishes independently, then it satisfies both 3.13 and 3.7. So it therefore follows that we can now see that since, of course, all these are equal to 0, then we can now say that this is equal to 0 and this is also equal to 0. So these are referred to as the Monge's subsidiary equations. So these are how we reduce them. Then, so we refer to this as the Monge's subsidiary equation. So we now assume 3.14 is reasonable into factors. Thus, we can have our dy minus my dx to be equal to 0 and dy minus m2 dx to be equal to 0. So the first equation in 3.16, that's this combined with 3.13 with du is equal to p dx plus q dy will yield an integral of the form g1 equal to a, h1 equal to b, in which a and b are arbitrarily constant. Then a relation of this type, where this f here is just an arbitrary function, or will be an arbitrary integral. So this is called an intermediate integral. That's this f here. Then similarly for h2, we can also have this, and then this f2 here also is arbitrary. So solving 3.17 and 3.18 will obtain p and q in terms of x and y and u. So these values of p and q are then substituted into du is equal to p dx plus q dy, which on integration yield the required solution. So we however here note that if 3.16a here is perfect square, it is convenient in some cases to compute only one intermediate integral. So that means you may not necessarily have to compute this and integrate with help of Lagrange's method to get the complete solution. Of course, you can use the Lagrange's method that we discussed earlier to get the solution of just one of the parts. So then this brings us to general form of second order PDE with variable coefficient admitting a first integral and its solution. So in this section, we have a relation of this form, h equals to f of g, in which g and h are differentiable functions of x, y, p, and q, and f an arbitrarily differentiable function, which is called the first intermediate, as we have explained earlier, of a second order PDE, if the latter is obtained by eliminating f and f prime from 3.19, that is from here, then together the relation obtained by differentiating 3.19 partially with respect to x, with respect to y also. So we now discuss the general form of second order PDE if admitting first integral and its method of solution due to Monge. The Monge we have earlier explained. So now, of course, from what we did, we can infer from what we did yesterday. So here now, by the time we differentiate our 3.9, that is this 3.19, I mean, we differentiate this equation here with respect to x, then with respect to y, then we are going to obtain what we have in 3.20 with respect to x and 3.21 with respect to y. Then we then eliminate f prime of g as we did yesterday by eliminating di phi, di x, and di phi, di y. We also do the same thing here, and once we did that, we are going to have this equation in 3.22, which is 3.22. And then we have our r, then we can group them together, then we have our r to be equal to, of course, we know what this is. This is di g, di p, di g, di p, di h, di y, minus di g, di y, di h, di p. That is how we have all these. And so by the time you expand what we have earlier, so we are going to have our r to be, we are going to equate our r to be this, s to be this, and then we have, what is it called? We have our t, then we have our u, and then v. So that is how we are going to obtain all these, what is it called, that appeared in this place, rs and t. So that is how we obtain that, and then our v. Hence 3.2 is the most general form of second order PDE that possesses a first integral. So then we thus proceed as Monge's method for solving equation of this kind by determining the first integral. Yeah, then we recall our Monge's method. We recall that dp, yeah, just as we said earlier, we can still remember this equation earlier. dp is equal to di p di x, that is by taking the total derivative of p with respect to x with respect to y. We are going to have this. The same thing, we take that of q with respect to x with respect to y, and we are going to obtain this equation. And we have said it, so by the time we reduce this, we divide through by this, we also divide through by this, we are going to have our r to be equal to this, and t to be equal to what we have here. Then, putting 3.26 into 3.22, we obtain, that is, we are now going to put all these, what is it called? We are now going to put them into the earlier equation. And doing that, this is what we are going to have. This is what we are going to have. And by the time we resolve all these denominators, we are going to have this, then we'll move on to this. By the time we separate them just as we have done earlier, then we have this. Then we can now say that we can now equate this to 0 and equate the other one also to 0. And that is what brings us to what we have here in 3.27b. This equal to 0, both sides. This also equal to 0. Of course, if this is 0, this is 0. By the time you put the two of them together, you will surely have 0. So in view of the presence of the term this and this, of the term u dp dx and u dq dy, n cannot be factorized. So we may, however, try to factorize n plus alpha n to be equal to 0, where this is an undetermined multiplier. So that is, in a case where this n is not factorizable, that is where we cannot factorize this particular one here, then we have to introduce this concept. And this is what we have here. You can see, then we multiply it by this so that we now have what we have here. So then we have this equation. So by the time you compare 3.29, that is, by the time you have introduced that factor now, and 3.33, you will see that this will be equal to this, and k here is equal to m, and we have r lambda divided by k to be equal to u. That's what we are going to have. So eliminating k, as we have always been done when we observe that we are going to obtain this equation 3.34. And then we recall that 3.34 has in general two roots, alpha 1 and alpha 2. If you look at it very well, you see that these are a quadratic equation in what was it called, in alpha squared here. Then putting alpha to be equal to alpha 1 and k to be equal to m to be equal to this in 3.30, then we have this equation. You can see. Then similarly, replacing alpha with alpha 2, we are going to obtain this equation also. So then we now obtain two integral of the form g1 equals to a1, h1 equals to b1 by solving the pair of lambda equals to lambda 1 and k is equal to m equals to r lambda 1 divided by u, and the integral of the type g2 equals to a2, h2 equals to b2 will be obtained from the pair of lambda 1, lambda 2. Hence, we get the two integrals of the type h1, which is equal to f1 g1, h2 f2 g2, where f1, f2 are arbitrary. So these are solved to determine p and q as functions of x, y, and u. Thereafter, we substitute into du equals to p dx. Then we have this equation, which when integrated by the time we integrate this equation here, we are going to have the solution for u here. So then implementing these procedure, these are some of the key things that we notice. So implementing this procedure, what we have just done, then we note the following conditions. One, if 3.34 has double root, that is alpha 1, alpha 2, it is only possible to obtain one integral of this from h1, which can be obtained from g1 equals to a1 or h1 equals to b1 to give the value of p and q to render this integrable. That's this. Then since this and this, if they are the same thing, then we get a more general solution by taking linear relation of g1 and h1 in the form g1 is equal to mh1 plus n. That is, if we have equal root, and integrate by Lagrange's method. Then if the first integral h1 is equal to f1 g1 and this, and unsolvable for p and q, then one of the first integral, which is this, may be combined with this or this to determine the value of p and q. Then integrating this differential equation, then we obtain the complete solution. That's another one. So these are the three things we note during the course of implementing the Monge's method for determining this thing. So we'll stop here for today. Then we'll continue with the next session tomorrow, which is going to be the fourth session. And the fourth session will span tomorrow and next tomorrow. So thank you all for